principal diagonal matrix with the principal diagonal equal to the eigenvalues. Similar manner to all of this, this is what's gonna happen with the main slides. Back to the main slides once more. All the differences, there is no differences between what you saw and the theoretical background supporting all of this. So let's start. In this section, we consider only the linear maps from n-dimensional vector space E to itself. So I'm moving from R3 into R3, R2 into R2, and so on. Okay, I'm searching for a vector, which is U, that's once you multiply it by A, you will have a certain value. Once you multiply by this vector, they will be equal to each other. This value, constant value, is the eigenvalue, and this vector stands for the eigenvector. Once more, U doesn't equal to 0, so if you are trying to get the equation, we are just explaining that the vector x or the vector u is gonna be a column vector. So just a second, this is the equation that I told you about. Just moving lambda u to the other side, you will have a minus lambda in times u equal to 0. This part of this matrix is the characteristic equation, and after you solve this characteristic equation, you will end up having your eigenvalues. Eigenvalues is given, you can get simply the corresponding eigenvectors. Okay, let's take an example, exactly the same, which is negative 1, 1, 1, and negative 1. I will try to solve it with you. I'm trying to hold it and solve the same steps, same everything with you once more, just to see how things are getting nicely together. It's really very simple part. Long, but it is simple, and you can do it for sure. Okay? I'm gonna solve this problem, and that's it for today. Okay? But just try to keep up with me. I'm sorry for being long, but it's really very important. Okay, so let's go once more. I will get to the characteristic equation, which is simply states that a determinant of A minus lambda I equal to 0, which is, as you can see, it's a negative 1 minus lambda, negative 1, positive 1, okay? This is positive 1, negative 1 minus lambda, and this determinant equal to 0, as I told you. Try to expand it, so you will end up having the following, which is 1 plus lambda to the power of 2, then minus 1 equal to 0. Try to expand it, it's gonna be lambda square first, second times 2, which is gonna be 2 over lambda. The last square is positive 1, negative 1 equal to 0. Take lambda as a common, so you will have lambda, which is gonna be lambda plus 2 equal to 0. That's lambda 1 equal to 0, and lambda 2 equal to negative 2. These are the two values of the eigenvalues that I told you about. In a similar manner, you will find this in the slides, exactly the same. So determine the eigenvalues and the eigenvectors. Eigenvalues of A, similar to what we talk about, you will end up having lambda plus lambda plus 2 equal to 0. So you will have lambda 1 equal to 0 and lambda 2 equal to negative 2. In a similar manner, I want you to do it exactly like as we saw together. So I'm gonna separate this part. Now I want to get u1, which corresponds to lambda equal to 0. Then I will get u2, which corresponds to lambda 2 equal to negative 2. Once more, I will regain the system, which states that I will have a matrix, okay, on this form. The elements are negative 1 minus 0, 1 and 0. The second row is 1. I'm here. Negative 1 minus 0. Negative 1 minus 0 and 0. So the system that I'm trying to solve is a homogeneous system, as you can see. And it is negative 1, positive 1 and 0, 1, -1 and 0. There is a relation connecting these two rows. Just to get the sum of these two rows together, you will have the following, which is 1, -1 and 0. All of these are zeros. Now, once more, this is vector, eigenvector 1 first component, eigenvector 1 second component. Try to get the equation, okay, by simply expanding this row. So it's gonna be u11 minus a u over 1, 2 equal to 0. That's u11 equal to u12. So the first vector will consist of two components, u1 sub 1, u1 sub 2. Make the substitution, which is going to be u12 and the u12. And for the first vector, which is, that's the first vector, u1 will equal to a 1 and 1. This is the first vector. Exactly in a similar manner, I will do the same, but this time I will do it with lambda 2 equal to -2. It's exactly the same. So it's going to be -1 minus of this lambda. So it's going to be plus 2, 1, 0. Similar manner, this is positive 1. This is going to be once more -1 minus the value of lambda, which is plus 2 equal to 0. And this will develop this eigen, or this matrix, which is going to be 1, 1, 0, similar to 1, 1, and 0, just trying to get to as close as possible to a reduced echelon form. So all I have to do is, as I told you, to multiply negative and adding. So 0, 0, and 0. This is 1, 1, and 0. This is the second vector first component, second vector second component. So it will lead to u21 equal to u2 of 2. Make u2 equal to any number. So this is the second vector. These are our components, u21, u22. Make this substitution. So it's a u22, u22, which is simply 1 and 1. Of course, there is a mistake here, because once you expand this, it's going to be u equal negative, so it's going to be negative, this is going to be negative. Look at this vector, and look at that vector. Remark that these two eigenvectors are orthogonal. The first vector, which is, I'm just trying to write it here, which is going to be 1 and 1. The second vector, which is simply -1 and 1. And as you can see, u1 dot u2 equal 0. They are orthogonal. Also, the model matrix, or the also normalized model matrix, I can write it like this. This is the elements of u1. Those are the elements of a u2. I can normalize it by dividing on the square root of the sum of the square of these components. So this can be simply divided by a root of a 2, also root of a 2, same way like a root of a 2, a root of a 2. If you get the transpose of this matrix, it's gonna be the inverse. So u transpose is gonna be 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2. معايا يا شباب؟ Okay, so simply if you get u times u transpose or vice versa, it's gonna equal to a unit matrix. And if you got u times the matrix A, which we started with, -1, 1, and 1, -1, times u transpose, the result will be a diagonal matrix with the values as the principal diagonal, 0 and -2, and the remaining will be found. Okay? So mainly this is the main steps that I told you about. Here we go once more. This is the quadratic equation. Trying to get lambda 0, making the substitution to identical rows, trying to solve this system of equation, you will have a relation connecting these two values, y equal to x. So the vectors that we are talking about, this is the base of this vector space of this solution, which is 1 and 1. Exactly right. Similar manner for -2, you will end up having x equal to the negative of y. So if you consider it as 1 or 2 or whatever, you will have 1 and the negative 1. These are the two vectors that we spoke about. So note that the eigenvectors 1, 1, 1 and negative 1 are two linearly independent vectors of R2. Having two vectors, just write that one is not a multiple of the other. They are not multiples of each other, which means that they are linearly independent. The matrix A by 2, which is formed from these two columns or two vectors, which is 1, 1, 1, negative 1, as we saw, in the basis for R2 consisting of these eigenvectors. If you do exactly the same with a 3 by 3 matrix, it's going to be exactly the same. So getting the B minus lambda I, solving, taking the principal diagonal minus lambda, trying to solve this quadratic equation, you will have three values. Lambda equals 0 and distributed 2 times. Lambda equal to 6. Making the substitutions exactly the same. You will have the eigenvalue, the first of them, subtracting 0 from the principal diagonal. Here we go. And trying to find the relation. Here I have x equal to z, and it's exactly the same. So now I have x equal to z, just substituting and getting the value of your the value of your eigenvalue, which is going to be 1, 0, 1, 0, 1, 0, 0, 1, 0, as we did previously many times. And for lambda equal to the second value, which is 6, you will end up having a system which, from trying to reduce to the reduced echelon form, x equal minus z and y equal 0. In a similar manner, this is going to be the basis for this solution, which is -1, 0, and 1. Guys, thank you very much. Try to regain these problems once more. And I hope you understood these steps. Please try to go through them carefully, and you will find the solution very, very simple. Thank you very much. Appreciated to be with me. And if you have any questions or something, we can answer it on Sunday, inshallah. Thank you very much. Enjoy the rest of your day. Enjoy your weekends. Bye.